Swayam Prabha. Digital India. Educated India.
Hello and welcome back to this lecture series on computational foundations of cyber physical systems. So, this week we will be starting with Kalman filters, how they are used for state estimation in cyber physical systems, and several other applications also exist for Kalman filters. So, just to have some recap, what we have here is this was my standard example of cyber physical system examples, right. And so, this was our course organization, right. So, till date we have actually covered all these topics up to week 10, and we have learned about basic control design, how to model the formal methods part on hybrid automata based modeling and reachability analysis. We have learned how to analyze complex nonlinear CPS using Lyapunov stability and barrier functions, how to design optimal controllers using quadratic expressions and stuff like that, and how to actually use neural network based controllers also. So, one important thing that we did not talk about there is, even we speak of optimal controllers like LQR and several other kinds of controllers like model prediction and others. So, they are based on optimization functions, and we have shown how such optimizations can be solved in real time. But in many cases we also assume that the full state of the system is known to the controller, but it is unrealistic. So, it is also possible in many cases that the full state is not known. What you have access to is just a set of measurements about the system. So, this is precisely where you need to understand that from such measurements how one can actually estimate the state, and this is where the role of observers or predictors and estimators will come in, and Kalman filter, as it happens, is one such widely used state estimator. So, this was invented by Professor Rudy Kalman long back, and it has till date it has found widespread application into domains of control and several other interesting electrical engineering discipline oriented domains. And so, we are just trying to give you a mathematical derivation of Kalman filter here, and we are just trying to show you how it is to be put in practice. Let us remember that this is a quite involved topic. There are a lot of deep mathematics and complex foundations of this topic, but we are just taking a simple linear algebra approach, and we are trying to figure out how the basic Kalman filter equation can be derived. So, that it will be our approach here during this coverage. So, it is an optimal estimator in case of assuming Gaussian noises, right, and it is trying to infer parameters of interest from inaccurate noisy observations. Okay. And when we say noisy observations, we are assuming that the noises are Gaussian, okay, and it will minimize the mean square error of these estimated parameters. Due to such Gaussian modeled noises, whatever is the error coming out in a mean square form, that an expression will be created, and we will try to figure out what is the exact filter which minimizes that expression. So, that is the basic approach here. So, in general, how is state estimated and how are such state estimates put into practice? So, typically that is how the control works. So, suppose let us assume that you have indeed designed such a Kalman gain or a Kalman estimator, okay, and your original controller is having some gain k. Okay. So, typically this is how you put it into practice. You will have the open loop plant. So, this is your plant. You can see that this is in the form of Ax plus Bu, right. Xk plus 1, the update is happening based on Bu plus Ax here, right, and you are getting the measurement y equal to Cx, and this measurement comes to your Kalman gain, right, and so this is part of the observer circuit here, and what it is, this circuit is entirely working on the estimates of the system, like you can see. So, if this is the estimate xk plus 1 based on the previous estimate, then what we can write is xk plus 1 hat is equal to A xk hat plus B uk. Okay. xk plus xk hat plus B uk plus L multiplied by this difference, that is the error between yk and the measurement estimate that the observer can generate. Okay. So, L yk minus yk hat minus yk, where this uk that we have, what is what really is it. So, this uk is in this case uk happens to be nothing but this controller gain k times the reference r minus x this estimate of x here. Okay. In case your reference is 0 in this place for the controller, so it is simply our standard equational form, that is minus k x k, but instead of minus k x k you are having minus k x k hat. So, that is the more practical scenario, because we can't expect my controller, like I was saying, that it is going to have access to x k, right. So, for all practical purpose this controller will have access to x k hat, and this observer is the system which is responsible to generate these estimates x k hat recursively in each step based on its sampling of the measurement y k. So, this is what you observe, and through this observer this is the estimate you generate, and this observer, as you can see, it is kind of mimicking your original system through the structure of A and B's, right. But along with that what you have is L, which is the Kalman gain. The entire purpose of this gain is to kind of minimize this difference, right, and it will try to figure out a nice estimate of x, so that based on x k's estimate, if I derive a y k's estimate, the difference between y k hat and y k must be very small. Okay. So, that is how this entire equational setting comes in. So, this is my observer, as you can see, and it is generating x k hat, and like I said, for all practical purpose this is x k hat is what the controller will take as input, because it will ideally not have access to the x k's. Okay. So, we will have some assumptions here, like you will have noises disturbing the system. For example, for the measurements you see y k equal to c x k, you are adding some noise here E k, right. So, this E k is a measurement noise, and similarly if you see, this is your evolution equation of the state, and for this evolution of x k you have also added one noise term, that is V k. So, that is your process noise. So, you are considering this V and E, the process and measurement noise, as discrete time Gaussian white noise processes who have some 0 mean, and their variances are like this. So, you have the variances and covariances given by these terms. So, variance of process noise is R 1, variance of measurement noise is R 2, and their mutual covariance is R 1 2. Also, you will have the initial state of the system x naught assumed to be Gaussian distributed with some mean m 0 and a covariance value R 0. Okay. So, overall, from this picture of actual deployment, that how the system is really going to work with an observer that is generating these estimates, I can write this update equation, right, because you see this is how I am able to generate x k plus 1's estimate using a x k hat b u k, and I am expecting the Kalman gain to do a good job, so that it does try to minimize this difference. So, whatever is this difference between its measurement, that is a sampling, and the measurement that it estimated based on previous measurements. So, this residue value I am trying to think that, well, it is doing a good job, so that this measurement error is as small as possible here. Okay. So, based on this we can write this update equation like I said. So, this notation, let me explain. So, what this means is that, well, based on the kth step measurement, we are trying to estimate x in the k plus 1th step, and it can be written through these equations, where I can derive this using the previous estimate of k x in the kth step, which was generated using measurements that were observed in the k minus 1th step, right. So, that is how I write this equation. And now, what do I have? I have two sets of equations, right, because I have this equation which is trying to kind of model the evolution of the state estimate, and as you can see, this idea of Kalman filter gain is coming as a multiplication factor or the gain corresponding to the residual, because this is my original measurement and this is my estimated measurement, and that gives me the residual, and I am using this to be to be handled by the filter here, and the rest of the dynamics is here, or that was there originally, and with this I am generating the estimate, right. So, this estimate and my original state, if I just subtract from the original state the estimate, what I can write is a reconstruction error, right. So, let x tilde denote the reconstruction error. So, essentially I can write something like this, right. I mean, well, how it comes is very simple. Okay, let me just correct the orientation of the writing here. So, if I just apply the first equation for the state update, and then I have this equation here. Okay. So, with these two, as we were discussing, let us look at the situation that, well, how I can really construct the reconstruction error here. So, we already have these equations of the next state with respect to the system model, as well as using the estimate with respect to the estimator, right. So, let us proceed from there. So, this is a reconstruction error which is minus the estimate. Now, if we try to do this math here, so we will reproduce the original state update equation. Here goes the process noise. Now, we will replace this estimate by the update equation of the estimator. We are for the time being so reproducing this thing here. And the estimate of the previous step goes in here. So, that is pretty much it. So, this is the residue which gets multiplied by this Kalman gain which we are supposed to design. So, if we now simplify this equation, let us see what we get. So, of course, these two will get cancelled out and this 2 gets combined in here, and you are left with the Kalman gain multiplied by the residue term. So, now you see if this is your reconstruction error in the k plus 1th step, then the reconstruction error in the kth step is this, right. So, we are doing something like, so this is same and the process noise remains, and as you can see we have added a term LK CXK and here, and again subtracted it to create this form here. So, that now if you see this is again kind of the reconstruction error. So, I can write this thing, I can write this entire dynamics of the reconstruction like this. So, that is the intention, okay, for why I am writing it in that way. So, this is how this derivation comes, right. So, as you can see this is what we have here, right, A x k tilde plus v k minus L k y minus this c k here. This is the x actually. So, if you recall, this is nothing but my measurement noise here, right. So, that is how we defined the measurement noise. So, that is why we can start writing it like this through the E k, and then if I write it in a suitable matrix form, I can write it like this, right, x k plus 1 tilde equal to I, the identity matrix minus Lk in a vector form, I have A and C in terms of, so xk plus 1 is getting expressed in a dynamical equation using xk with the additive term of the two noise values, right. So, that is like a nice matrix vector representation of the dynamics of the reconstruction here. So, this is what we intended to do here all the time. So, that is the derivation and that is how it is happening. So, just to recall, yeah, this is where we had Ek being defined, right. So, fine, just recall that this is, yeah. Now, if we just go forward, so let us understand what we are really trying to do. So, I mean we have set up a template equation here, right, an equation which is which is set up with the objective that it will give me an estimate of x based on some previous estimate, and the estimate should be defined in such a way that it minimizes the error between the estimate and the original value, right. So, the idea is that we will define an objective function which will minimize this estimation error here, and the condition of the minimization should be such that that will give me this gain value L. Okay. So, that is how the Kalman filter is indeed defined here. So, this is my objective, then I want to minimize the variance of the estimation error, right, because it is an error, right, it can be positive or negative. So, in the long run I want to do a least square minimization. So, I am going to minimize the variance of this estimation error